Got three examples that I want to run through you with here. And all of these examples, what we're going to get used to doing is we're going to get used to applying these helpful trig limits that you see here on this slide. Most notably, we're going to notice that we come across a lot of patterns where we're applying this limit here and this limit here. So to give you an example, here I have the limit as x approaches 0 applied to the function sine of 2x over 3x. I know that one of my helpful trig limits is the limit as x approaches 0 applied to the sine of x over x, which equals 1. What this basically means is it'd be nice if I had a rational function right here where I have the sine of something over that same something. If I could create that ratio, apply this limit as x approaches 0, I'd get 1 back. So looking at what we have on this problem, I've got the sine of 2x over 3x. So as I mentioned down here, I want this piece to be the same as this piece. I don't quite have that here because the argument on my sine function is 2x. Down here, I've got a 3x. I'd rather have a 2x down here. Well, we can create a 2x. We can do that in the denominator by multiplying by 2. We've already got the x we need, so now I just need a factor of 2. Now, obviously, I can't randomly just do that to the denominator. I have to also multiply by 2 in the numerator. Now, through some shuffling, I'm going to rewrite this limit problem as the limit as x approaches 0 applied to the ratio that I'm looking for, which is the sine of 2x over 2x. So basically, I've taken this piece right here and put that over this grouping right here, meaning the leftover factors I have in the numerator, I've got a 2 up here, and in the denominator, I have a 3 down here. So I could tack on a 2 over a 3. Now when I apply the limit as x approaches 0 to this portion right here, well, that takes me back to my helpful trig limit over here of 1. I know all of this is going to equal 1, which I'm now multiplying onto the 2/3, meaning the limit as x approaches 0 applied to the sine of 2x over 3x must be 2/3. So now in a similar fashion, let's look at the limit as x approaches 0 applied to a rational function where we have the cosine of 4x minus 1 over 7x. Going back to my helpful trig limits, I know if I take the limit as x approaches 0, I apply that to 1 minus the cosine of x over x, or to the cosine of x minus 1 over x, that's going to give me 0 back. So kind of like the last problem, I want what's my argument right here on the cosine function to match up with what I have right down here. As you can see from how this problem's set up, my argument on the cosine function is 4x. I would like there to be a 4x down here. So since it's a 7x and not a 4x, since I at least have the x, all I have to do is multiply the bottom by 4 and multiply the top by 4. If I rewrite this now, I have the limit as x approaches 0. I'm going to shuffle things around here to make it more consistent with this helpful trig limit. When I shuffle things around, I've got the cosine of 4x minus 1. There's that top piece I need, so I'm using this part right here. On the bottom, I'm going to have a 4x, so I'm lumping those factors together. The factors which remain then would be 7 and 4, so I will tack on to the end of this 4 in the numerator, 7 in the denominator, or 4/7. And now if I look at the formation right here, as I apply my limit as x approaches 0 to the cosine of 4x minus 1 over 4x, that's consistent with this helpful trig limit, meaning everything I got in the box there must go to 0. That 0 is being multiplied to the 4/7, which remains. If I do that multiplication, I can safely say that my limit here is going to be 0. So it would make sense if we're doing examples here to conclude with an example that involves both sine and cosine functions. So what I've done here, I've set things up very similarly. I brought my helpful trig limits along to assist. I made a minor tweak here on the helpful trig limit I know that revolves around sine. Initially, I've taken the limit as x approaches 0. I'm applying that to the sine of x over x to give me 1. Well, as it turns out, if it's x over the sine of x, that will also give me 1. So now looking at my initial problem here where we're taking the limit as x approaches 0, we're applying that to 1 minus the cosine of 7x over sine of 5x. Let's look at the arguments on the trig functions. With the cosine function, the argument is 7x. So since I have 1 minus cosine of 7x in the numerator, it'd be really nice if I had a 7x somewhere in the denominator. So I'm going to kind of force the issue here. I'm going to multiply on the bottom a 7x. At the same time, I have to multiply that to the top. Now when I look at the argument on my sine function here, that argument is 5x. Well, it'd be really nice if I had the 5x in the numerator, since the sine of 5x is down in the denominator. So force the issue, put a 5x up here. If I multiply by 5x to the top, multiply by 5x to the bottom, I can create these little pieces that I need. Okay, now we're going to rewrite everything before we actually apply the limit. So in my next step here, I'm going to bring this down just a little bit to fit on the screen. Take the limit as x approaches 0. Let's start with this 1 minus cosine of 7x up here. 1 minus the cosine of 7x. It'd be really nice if that was over 7x. So I can do that because I'm accounting for this piece in my numerator and this piece in my denominator. Now, as far as the sine of 5x is concerned, well, my sine of 5x, that can be the denominator in a new rational expression I'm going to set up over here. And I'm looking to have a 5x on top, so I can put a 5x on top because I got a 5x right here I can match up. And now I've got these little formations I need, inspired again by my helpful trig limits over here. So we'll apply the limit to all this in just a moment, but we still have to account for these remaining pieces. We've got a 7x and we've got a 5x. Well, if I've got a 7x in the numerator, a 5x in the denominator, I can just write 7x over 5x. And since I'm sharing common factors between numerator and denominator here of x's, I can go ahead and cancel those out. They really aren't relevant anymore. So now, as I apply my limit, I'm taking my limit as x approaches 0. I'm applying it to these helpful formations, we could say, with the trig functions. I know when I take the limit as x approaches 0 and apply it to this particular part, what this is all going to equal, it's going to equal 0. I know that from right here. As far as taking the limit as x approaches 0, applying it to this part, well, I know that's going to equal 1, and that was being multiplied on, so I'll multiply 1 on. That's coming from this part. As far as what remains, well, we had that 7/5 that remained, so we tack that on. And now we can see how this plays out. It's 0 times 1 times 7/5. My answer is just 0.